Okay, last video, number 4 of 4 here. So let's talk about momentum for this one. Our old linear version of momentum looked like this. So momentum was just mass times velocity. What is momentum? Momentum, and I just realized in the energy one, we never give a definition to kinetic energy, which is kind of hard to do. But kinetic energy is kind of like how much stuff something that's rotating could do, like how much damage it could do or whatever. Momentum is a measurement of how much something wants to stay moving. All moving objects want to stay moving, but some want to stay moving more than others. So the more mass you have, the more you want to stay moving. The more velocity you have, the more you want to stay moving. So the equation is momentum is mass times velocity, and it's measured in kilogram meters per second. We've never given that a special name in physics. So you can probably guess what it looks like for angular momentum. Angular momentum, which is symbolized by capital L, think of it as for angular. The mass gets replaced, as it always does, with rotational inertia, and the linear velocity gets replaced, as it always does, with angular velocity. Its units are kilogram meters squared per second, but I haven't seen that hardly ever actually come up and addressed. So something that is rotating wants to stay rotating, and something that's not rotating doesn't want to rotate, but not all things that are rotating want to stay rotating the same amount. So if you have more rotational inertia, you want to stay rotating more. And if you're spinning faster, you want to stay rotating more. A few things to sort of bring up then is if we think about the direction that something is moving. So if a block of ice is moving this way, not only does it want to stay moving, but it wants to stay moving that way. It doesn't want to move that way or that way or that way. So it is hard to get it to change that direction of motion. Likewise, if something is spinning, it wants to stay spinning that way. But the direction that we define this thing spinning is actually kind of weird. So you may look at this and say, like, oh, it's spinning counterclockwise. Even if I sort of let it keep spinning like this, but sort of tilted it up on its side here, and you're like, oh, well, it's still spinning the same way. It's still spinning counterclockwise. But that's not actually how we define it in physics. And I doubt this will come up, but just in case, we define the way something's spinning in a weird way in physics. So we take our right hand, it's called the right hand rule. So make sure it's your right hand. And you take your fingers and you curl them in the direction that the object is spinning. And so your thumb points in the direction that we say its angular velocity points. So if this wheel, like it was a record spinning this direction here, we'd actually say its angular velocity points up. And why that is important is if you imagine I take this thing and rotate it almost perpendicular to the page, now if I do the right hand rule, it's pointing towards me. So it's not spinning the same way actually. And so it doesn't want to go from spinning like this to spinning like this, even though we never changed the clockwise or counterclockwise way that it was moving. And maybe in class you remember when we moved the bicycle wheel around that it resists you trying to make that change. So that is the thing with angular momentum. And kind of going back to some of the stuff we've already talked about, because if you moved masses to the outside of the circle, you would increase the rotational inertia, then this thing would be harder. It would want to stay moving more is the point, because it would have a bigger eye there. So without any outside forces on a system, its momentum is conserved. And without any outside torques on a system, its angular momentum is conserved. Let me show you a few examples of that. Let's say we have an ice skater, so frictionless ice, so no outside forces. That means that the angular momentum of the system before any interaction is equal to the angular momentum of the system afterwards. Now when the skater's here, they have their mass spread out, a bigger radius. So they have a bigger rotational inertia, and they're spinning with some angular velocity, omega. But when they do this, they bunch themselves up into a tighter ball there, then their moment of inertia, their rotational inertia drops because their radius of their mass dropped. They're closer to the point of rotation. But remember, the total angular momentum can't change. So if one variable is dropping, but this has got to stay the same, then the other variable's got to go up. So the angular velocity goes up. And everyone knows this. If you pull yourself in tighter as you're spinning, you spin faster. You've all done that as a child on a swing where you wound up the chains and then started to spin out. And as you crunched yourself into a ball, you spun faster and faster and faster. And that is why. So that's the type of question they may ask in terms of angular velocity. By the way, the kinetic energy is not conserved here. It actually took work from your muscles to pull yourself in that would never happen on its own. And so that work causes your kinetic energy actually to increase. Another way that they might ask it is something like this. So maybe they've got like a disc spinning with some peg on top. This is the way I've drawn it. And let's say you drop a second identical disc on top of that peg there. So we were spinning with some rotational inertia I. Let's assume the peg is so light it doesn't really affect the problem. And it's spinning with some angular velocity omega. Well, let's say that second disc drops down there and there's no friction, no outside forces. Well, we basically just doubled our rotational inertia by dropping that second identical disc on there. So to keep the angular momentum the same, something's got to give. And that means we'd have to have half the angular speed that we had before. So maybe they would give you an example like that. So now what if there is an outside force from the system? Well, our old way of talking about it would be impulse. So impulse is defined as force times time, and that causes a change in momentum. The change in momentum is equal to the impulse, force times time. So again, it's a pretty straight. By the way, these equations, all four of them are on the equation sheet. The change in angular momentum is equal to, we replace force with torque, and time is still time. I wrote it differently here, but they're both times. So to change the angular momentum of a system, we need a torque exerted over a time. One more thing that they might ask about, they like these sort of balls thrown at a door or a lever or something. Let's say we have a door sitting here and you throw a ball at it with speed v. The door's at rest, it's not rotating at all, and the ball's thrown at it. Now some people think like, oh, well the door's not rotating, the ball's not rotating, it's going in a straight line. Nothing's got angular momentum, and therefore nothing could be rotating afterwards. But I bet you would also intuitively guess if you threw a ball at a door that had a very well greased axle there, the door would start to rotate, it would start to move. So here is the thing. We can actually think of a point mass, we will call this, as having angular momentum. And how do we figure out how much angular momentum it has? This is a little flip from all the other ways we did stuff. When we did velocities and positions and accelerations, to go from the angular thing to the linear thing, we multiply by r. But this time it gets reversed. To get the angular thing, we take our regular old linear momentum and multiply by r. So if we knew this thing's mass and we knew its velocity, we would know its regular momentum. And then we can multiply by the radius to get its angular momentum. So the further out you threw this ball from the axis of the door, the more we would define its potential angular momentum as. And therefore, greater angular momentum means greater spinning when it hits that door. That also makes sense from a torque standpoint, because this ball is going to exert a force on this door when it hits it, and torque says the more lever arm, the more radius we have, the more torque we're going to cause, and torque, as we just said, causes a change in angular momentum there. A type of question they like, and they like this both for linear momentum and angular momentum, is what if, let's take a couple different cases here of a ball that maybe it sticks to the door or maybe it bounces off the door and goes the other way. And they might ask you, well, in which case will the door be spinning faster? Well, when it sticks to the door, think about it like this. The ball was going that way or wanting to rotate things that way. So the ball's still moving in this case. So it's got some angular momentum. The total angular momentum of the system can't change. So if the ball still got some in the original way, that's less available for the door there. Then if the ball just stopped, imagine the ball just came to a dead stop when it hit the door and the door started to spin. Then the door would pick up all the angular momentum of the ball and it would spin faster. But one more quick thing here is, what if the ball bounced back the other way? Well, then this door would have to spin even faster than the two other cases. Why? Well, because we had momentum that way. Or you can think of it as rotating that way. Now we're going this way, or rotating the opposite way. So if the momentum of the system can't change, it's not like the ball just went from something to zero, or in this case, from something to something smaller. It went from something to something negative the other way. So for the door to keep the angular momentum of the system a constant, it's got to pick up even more angular speed than it did before. Sort of keep this in mind. Bouncing always causes bigger changes in momentum than coming to a dead stop or sticking.